Welcome to another chemistry MDCAT video for A-level students. This time we will be tackling a worksheet from the organic chemistry topic. So, which of the following does not give a yellow precipitate with iodine and NaOH? Acetone, it does. Acetaldehyde does. Benzaldehyde does not. Acetophenone does. You should be familiar with the structure of acetophenone. If you're not, please Google it. Which of the following does not give a brick red precipitate with Felling? Formalin does, because formalin is an aldehyde. Acetaldehyde does. D-glucose does, because it is an aldo portion. Acetone does not. Now, formalin has been specifically mentioned in the book and in parts of the syllabus which are usually tested. It was formalin is actually formaldehyde in water. So when we attempt to make formaldehyde in the lab, we make use of methanol, and we also use certain catalysts like silver and copper, and what we get is a mixture of water and the formaldehyde, which we call formalin, because it's about 40% formaldehyde, 52% water, and like 8% methanol, which hasn't quite reacted. There's also obviously oxygen involved. That is sort of like pumped in. So I think we ought to revise that portion of the syllabus. If you have your books with you, it would be a great help to you if you take a look right now. The best way I think about going through the UHS is that when you think about something, you should immediately check it out, because you don't have a lot of time. We end up forgetting stuff. In A-levels, we had a whole year, plenty of stuff. We don't right now. Page 228 of textbook 2. And yes, formaldehyde is made in the laboratory by passing a mixture of methyl alcohol and air over copper or silver catalyst, and if another catalyst which can be used is platinized asbestos, and the temperature is about 300, and because of that we get formaldehyde and water. Air is drawn through the methyl alcohol with the help of a suction pump. Methyl alcohol is oxidized to gaseous formaldehyde, which is absorbed in the water that is produced as a byproduct. The resulting mixture is formalin. Formalin is a mixture of 40% formaldehyde, 8% methyl alcohol, and 52% water. Obviously, formaldehyde can also be made in an industrial scale, in which case we need a higher temperature of about 500, and formalin is not produced. We get pure formaldehyde, and we have to use different, more efficient catalysts like iron oxide and molybdenum oxide. So similar reactant vapor and air over iron oxide, molybdenum oxide, or silver catalyst at 500 degrees Celsius. So that is how you prepare. Now there is another way of making acetaldehyde, and that basically makes use of salts of formic acid and that of acetic acid. To be more clear, the calcium salts of formic acid and acetic acid are reacted together in a process known as dry distillation, and you get two products, one being acetaldehyde. Previously we got formaldehyde, now we're getting acetaldehyde, and the other one is calcium carbonate. You can also make acetaldehyde from ethanol via the use of sodium bicarbonate, sodium chromate, and H2SO4. Now you can also make acetone, but for that you just need the calcium salts of acetic acid. You also use dry distillation, and you also end up with calcium carbonate. So anyways, I find that this method is pretty helpful. So which is the most difficult to oxidize? This over here is methanol, or I can't really remember what it's called at the moment. Formaldehyde, it's easiest. Then we have acetaldehyde, we have acetone, and we have propylaldehyde. And acetone is the most difficult because you can achieve the rest of them with the use of, say, some sort of a somewhat weak oxidizing agent, even with the help of Tollens reagent or Fellings. But for this to happen, you need the strong stuff like acidified sodium dichromate, acidified potassium permanganate, or concentrated HNO3. And the way the oxidation happens is pretty cool. This is like at the end of the topic. Ketones do not undergo oxidation easily, and if they ask you the reason, it's because the oxidation of a ketone involves the breakage of strong carbon-carbon bond, and they have no reaction with mild oxidizing agents and are only oxidized by strong agents such as K2Cr2O7 H2SO4 or KMNO4 H2SO4 and concentrated nitric acid. In the oxidation of ketones, only the carbon atoms that are adjacent to the carbonyl group are attacked. So they can ask you if, exactly which points are attacked during ketonic oxidation. And the carbon atom that is joined to the smaller number of hydrogen atoms is preferentially oxidized. And in case of symmetrical ketones, only one carbon atom adjacent to the carbonyl group is oxidized, and a mixture of 2 carboxylic acids is always obtained. So if they ask you that if you have a symmetrical ketone, how many carbon atoms are oxidized, your answer will be just one carbon atom is oxidized in the case of a symmetrical ketone, and said carbon atom is one that is adjacent to the carbonyl group. And if it's asymmetrical, only that carbon that is adjacent is oxidized, which has the smaller number of H attachments. So this is important. So next, the alcohol which does not give a stable compound on dehydration is ethyl alcohol. I guess it does pretty well. Methyl alcohol does not give a compound at all. N-propyl alcohol does pretty alright. Same with N-butyl alcohol. So let's go with methyl alcohol. The reaction of C2H5Cl plus KOH to form C2H5OH plus KCl. This is obviously a nucleophilic substitution. Which reagent will perform the following? As you can observe, this is a reduction. For an aldehyde, what sort of an agent do we need? NaPH4 works just fine. In general, we do not make use of the nickel hydrogen combo. We can learn about this in reduction. There is a topic on that. Reduction. both aldehydes and ketones can be reduced. This can be a question even. And aldehydes are reduced to primary alcohols, whereas ketones are to secondary. The carbonyl group in both cases is converted into an alcohol group, and both need sodium borohydride, and if they ask you, the reaction is carried out in 2 steps. You don't need to know the mechanism, and the reaction takes place under anhydrous conditions, and then the first step and next one is a hydrolysis. And the sodium borohydride reduces the carbon-oxygen double bond, but not the carbon-carbon multiple bond. That is important and what distinguishes it from the reduction of cyanalkane. Aldehydes and ketones on reduction with hydrogen in the presence of a metal catalyst like palladium, platinum or nickel form primary and secondary alcohols respectively. Hydrogen is added across the carbonyl group. My apologies, it's actually both P and C. Again, this is something I believe is worth writing down in case we forget. You're hosting me because I did it wrong this time. So if you have a notebook with you, it's a good idea to sort of like use that as your database for all the stuff you find difficult or such. You may even keep a file or something, whatever suits your taste. And you can like make a small note. Aldehydes plus ketones reducible via H2 can be with nickel, platinum or with palladium. All 3 catalysts work just fine. Anyways, you don't need to go into the detail. You just have to know that this is a possibility. Organic acid without a carboxylic acid group is lactic acid. Certainly has one. Lactic acid is actually you can even form lactic acid if you use methyl cyanide. If you use methyl cyanide, actually it's more like ethyl cyanide because I keep messing these two up. Hopefully you won't. So it's like this, right? You can make lactic acid with this. So if you ever forget what the formula is, just think about this, because when this is hydrolyzed, what happens is that there was this removal happens over here. Actually, I keep messing this stuff up. You firstly, you just have to start with propanol first, because that would explain where the alcohol group comes from. Propanol. So it's like this, right? Initially it's like this. And then what happens is that as the HCN portion sort of like approaches, there is this attachment. Oh, I hate this. There's actually an over here. We're actually starting with methyl cyanide starting with formaldehyde, right? And then there's this attachment over here that sort of like breaks the attachment over there, and we get this, right? Next step, we hydrolyze, so this becomes NO and we get an OH over here. So basically on the second carbon we have a hydroxyl group, so that's why it's alpha 2 hydroxy propanoic acid. And where this is found, I think it can be found in the carboxylic acids topic. We can take a look right now. And the carboxylic acids topic is, I think, the one that is right next to this one. In the preparation methods, they're given from alkane nitriles. Compounds that have a cyanide group are called nitriles, and hydrolysis of an alkane nitrile on boiling with either a mineral acid or an alkali yields carboxylic acid. So initially we get so they have actually done this, but it should really be in the aldehydes topic in more detail. The better details can be found in the aldehydes topic. There's a lot in the aldehydes topic that is not included, so you have to be really careful that you don't end up wasting your time with that stuff. Really follow what is written on the syllabus in terms of this topic. So page 233, and this is an important bit, the addition of HCN, and this is mentioned in the syllabus. HCN adds to both the aldehydes and the ketones to form cyanohydrins, and the reaction is carried out by adding slowly a mineral acid into an aqueous solution of sodium cyanide, and the acid generates HCN from sodium cyanide in situ. So we have formaldehyde and HCN happens, and we have NaCN and HCl making said HCN, and we get formaldehyde cyanohydrin. So basically we just add the name of the aldehyde in front of cyanohydrin in order to name it. I guess I find this to be fairly important. So if you have a pen and a paper and you're writing down points, I think this is something you should write down. This is a naming that has not been tested yet, I think, but you never know when they broach. And you get C, H, H, OH, CN, and the naming part formaldehyde cyanohydrin. One thing you got to remember is that nucleophilic addition can happen both to an aldehyde and a ketone. In case they ask this very simple but question that might out with all the studying we have been doing lately, our brain has been quite full, so don't forget the basics. Now the cyano group, and they've given other examples with acetaldehyde and with acetone, and the cyano group is hydrolyzed by an aqueous acid into a carboxylic acid through an acid amide. So firstly we will get an acid amide as an intermediate. We start with acetaldehyde cyanohydrin. So an acetaldehyde cyanohydrin will contain 3 Cs in total, and we have 2 molecules of H2O and NH2SO4, and we get 2-hydroxy propanoic acid, which is a lactic acid, and we also get NH4HSO4. And the reaction used in the synthesis of alpha hydroxy acids that contain 1 carbon atom more than the number of carbon atoms in the starting aldehyde of ketones. So this is important, acid amide intermediate. Let's not forget the acid amide intermediate. Firstly we will have a partial hydrolysis such that we will get an acid amide followed by a complete hydrolysis in which we will get the carboxylic acid, and the byproduct, which is NH4 HSO4 is also important. It's made alongside the acid. In both cases, H2 will be needed in both the steps, the one that makes intermediate and the one that goes from the intermediate to the final product. So it's not lactic acid. Oxalic acid is basically it's a diacid. So obviously vinegar is acetic acid. Now picric acid, one wonders what picric acid is. I think it's 2,4,6 trinitrophenol. So it definitely is an acid, but it doesn't have, and it's an organic acid, but it doesn't have the carboxylic acid group. So that is the answer. So I hope you're following and that you have the book with you. I think the best way for you to utilize this video is if you have the book with you and are checking out the stuff that I am checking out. So onwards. Which of the following statements is not correct about the alcohols? Does methanol evaporate quickly? Seems unlikely. Ethanol has stronger hydrogen bonding than that of methanol. Actually, no. It sort of weakens the bonding. The presence of the methyl portion. Ethanol is a weaker acid than water, definitely. And alcohols with less number of carbon atoms are more soluble. They certainly are. So that would make this the wrong one, as suspected. So have you checked out what picric acid looks like? You should. An organic compound A reacts with PCl5 to give P, right? And the compound P with sodium metal gives N-butane. This A and B are. This is irrelevant, I think. Now the question is, which of the following alcohols cannot be produced by treatment of aldehydes or ketones with NaBH4? The answer is 2-methyl 2-propanol. Propanol, because that is a tertiary alcohol, and neither aldehydes or ketones are made from tertiary alcohols. Bit of a trick question, but not difficult. Which of the following reagents react in the same manner with methaldehyde, acetaldehyde, and acetone? HCN, it certainly does. Ammoniacal silver nitrate, it won't. It will just with the first two. Copper hydroxide with NaOH, just with the first two. Copper hydroxide might not react with any of them. So which is more acidic in nature? Is it water? Is it phenol? Is it ethanol? Is it ammonia? The answer is phenol. Now if you look over here, and if we observe, as a result of reaction of phenol with bromine water, what is the product obtained? Well, we get 2,4,6 tribromophenol. Again, ALS students should not have a problem with this. Let's take a look at the next one. Which of the following is correct for the stability of the phenoxide ion? The resonating structure of benzene, the delocalization of pi electrons in the phenoxide ion, that is it. Which compound will give the most stable carbonium ion? Carbonium means cation, basically positive. the one that is in a tertiary formation ought to give the most stable one. So I would go with D. So next, which of the following does not give iodoform on warming with NaOH and I2? Acetone does, so does ethyl alcohol. And propyl alcohol unfortunately does not. Isopropyl can. Again, I would explain, but this is piece of cake for A-level students. Phenol is less soluble in water. Due to what reason? The non-polar nature of the phenol, the acidic nature of the OH, the non-polar hydrocarbon part in it, or the acidic nature. Obviously it's this part. So which of the following reagents is used to prepare ethene from ethanol? Let's think about this. Obviously this is a hydration. Do we need concentrated H2S4? We certainly do, because there is an initial attachment of HSO4 portion on one side and of H on the other side, and then in the next step this stage once takes place easily at room temperature. Next step, but which involves water, and 100 this portion is hydrolyzed and we get OH instead. Back to what we were discussing. Alright, how many pi electrons are there in a planar ring of phenol? That is 6. And aldehydes and methyl ketones form addition product with. The question is phenyl hydrazine. That is more of a condensation product. Hydrazine, hydroxylamine, sodium bisulfite. I don't think this is really part of the syllabus, but you never know. So let's take a look.